All right, let's talk about something we all deal with every single day, spam. We're going to pull back the curtain on the unsung hero that keeps your inbox from completely overflowing with junk.
I mean, have you ever really stopped to think about it? How does your inbox just know what's garbage? All those bizarre offers for things you'd never, ever buy? They just sort of vanish. It feels like magic, doesn't it? Well, it's not magic. It's actually some really clever math at work.
Okay, so the tool behind this magic trick is something called a Naïve Bayes classifier. For today, let's just think of it as a detective. A super fast, kind of quirky detective who has a very specific and, let's be honest, a little bit simple way of cracking a case. Now, every good detective needs a rule book, right? And this one's rule book is something called Bayes Theorem. It's basically just a formal mathematical way to update what you believe when you get new information. Think about it like this. If an email contains the word free, how much does that increase the odds that it's spam? Bayes' theorem is what lets us calculate that like exactly. And that brings us to the classifier itself and why it has that name, naive. It takes that powerful theorem and then makes one giant, kind of silly assumption. It pretends that every single word in an email is totally unrelated to any other word. So it doesn't get that words like free and money are a classic duo. To our detective, they're just two separate lonely clues. Now, obviously, that's not how language really works, but this little white lie is exactly what makes the whole thing unbelievably fast.
So you're probably wondering, why on earth would we use a detective that's so, well, naive? Well, here's the thing. That simplicity, it's its superpower. It is blazingly fast, and you absolutely need that when you're sifting through mountains of email every second. It's a total rock star for anything involving text, and what's great is that it doesn't need a ton of data to start being useful.
Okay, but this simple approach has a major weakness, a real glitch in the system. Our detective is a pro with clues it's seen before, but if you throw something totally new at it, it can completely freeze up. So picture this. A spam email shows up, but it has a word the model has never, ever seen before. You know, like a creative new misspelling of a common spam word. The model has learned from thousands and thousands of examples, but this one word is brand new. What do you think happens then? It's a total disaster. The whole calculation just collapses. See, the model works by multiplying the probabilities of all the words together. And what happens when you multiply anything by zero? The answer is always zero. So even if an email is packed with classic spam words, that one single unknown word with a probability of zero forces the final spam score to be zero. Our detective literally throws the entire case out the window because of one clue it didn't recognize. So, how do we fix this? How do we stop our detective from just giving up so easily? Well, thankfully, there's a really elegant little trick for this. It's called smoothing. It's often called Laplace smoothing, and honestly, it's brilliant in its simplicity. All we do is pretend we've seen every word one more time than we actually have. We just add a 1 to the count for every word. That means that even a brand new, never-before-seen word gets a tiny, tiny little probability score instead of 0. And that's just enough to make sure the whole multiplication thing never crashes and burns. Problem solved.
All right, so our detective is back on the case, ready for anything. It works. But now we have to ask the big question. How good of a job is it actually doing? It's time to give our detective a performance review.
And this is the classic tool for that review. It's called a confusion matrix. Now, it might look a little technical, but it's super simple. It just sorts all the predictions into 4 boxes. You've got your true positives, that's spam we correctly caught. Then true negatives, good emails we correctly let through. The other 2 boxes are where things went wrong. False positives are the good emails we accidentally called spam, and false negatives are the spam emails that managed to sneak past us. Now, using those 4 boxes, we can measure performance in different ways. The one everyone thinks of first is accuracy. It just asks, overall, what percentage of emails did we get right? Simple enough. But then there's something else, something really important, called recall. Recall asks a totally different question. It says, of all the spam that actually existed, what percentage of it did we manage to catch? It's all about how thorough we are. Yeah, and understanding this difference is so key. Let's put it this way. High precision means we're really, really sure that what we call spam is actually spam. We're being very careful. High recall, on the other hand, means we're really good at finding most of the spam out there. We're being very thorough. And here's the kicker. These 2 things are often in a tug of war. Improving one can sometimes hurt the other.
And this all leads to maybe the most important question in this whole process. What's the cost of being wrong? Which type of mistake is actually worse? Because believe me, the answer to that question changes absolutely everything.
So let's just break down those two mistakes one more time. A false positive, that's when a good email, like a job offer or a message from your boss, gets thrown into the spam folder by accident. A false negative is the opposite. That's when a piece of actual junk mail gets through the filter and lands right in your main inbox.
Now think about the stakes. For a spam filter, a false negative, getting some junk mail, is annoying but whatever, right? But a false positive? Missing that important email could be a huge deal. Now, let's flip the script. Imagine we're not detecting spam. Imagine we're detecting a life-threatening disease. In that case, a false negative telling a sick person that they're perfectly healthy is, well, it's catastrophic. The stakes just could not be higher.
And that's really what this all boils down to. When we build these kinds of systems, it's never just about chasing the best accuracy score. The real question we have to ask ourselves is, what kind of mistake are we more willing to make? It's about understanding the real-world consequences, and that choice turns a simple algorithm into something that's actually, well, deeply human.